Theoretic congruence, we're trying to show that there's either 0 or 1. Let's say 1. Let's spell 1, why don't we? Prime solutions. Or I'm just repeating the instructions here. Solutions abbreviated, okay? Now we're given that the GCD of A, which is sort of the constant here, and B is the modulus, is greater than 1. That means it's greater than or equal to 2. So right here we can write down D is greater than or equal to 2. Which stands for greatest common divisor, common letter. D is greater than or equal to 2. Okay. Now we're going to proceed here. We're trying to show again there's no more than one prime solution, which is equivalent to 0 or 1 prime solutions. So what we're going to do is suppose there's 2. Now if we reach a contradiction, that will prove our result. Okay, so now just some commentary right here on notation. This statement right here implies there is a, shall we call it D sub 1? A is equal to D sub 1 times D, and B is equal to, let's call it D sub 2. And again, we get in trouble with notation a lot of times. I like the subscripted stuff rather than making up different letter names. B is equal to D sub 2, let's call it. Right? That's the meaning of this, where D is the greatest common divisor. Okay, that's what that means. And so if you carry on here, I will use exactly that. We assume that there's 2 distinct primes, P and Q, common letters, that are congruent to A mod B. Here we have the 2 statements. Now this is another way to restate both of these congruences. P is equal to A times some multiple of B. Q is equal to A times some multiple of B. Now, if you do the algebra right here, the D's factor out. Okay, I use different stuff here, but it's the same thing. Okay, so the D's factor out, and what does this statement imply? That implies that the GCD, and I'll just call it. Some people don't like to write this as an ordered pair, but it's context sensitive here. So this means P, the GCD of P and Q has to be greater than or equal to 2. Okay, which is impossible, right? That's greater than or equal to 2 for the very same reasons we talked about 2 up here. Okay, and so that means this contradicts P and Q are prime. This contradicts the primality. Contra abbreviation because of this slow mouse operated by a slow human. Contradiction contradicts, I'll go ahead and spell it. Contradicts primality. And when I say primality, I mean, of course, of P and Q. Primality is the way you, I don't know, just a fancy, pretentious way of saying the noun form of prime, I guess. Okay, so that completes the proof. Let me put QED. Now, y'all, let's do a sanity check on this, just so this will make a little bit of sense. So we proved there is no more than one prime solution, which means there could be none. Now let's just do a concrete example. Let's say we have I don't know, 3 or n is congruent. Let's do this. N is congruent to 3, and let's do mod 12 here. I'll create a list here to make this more believable. So certainly 3. Now this would be the 1 prime if you want to create the list of solutions here, or a partial list. 3. Okay, so 3 is a prime number just by construction. Okay, now, so let's do 3, and then what? Let's just write down a few more here. 15, 27. And what they're saying forever and ever, and you can be formal about it if you want to, but 27, 39. Notice that all of these numbers afterwards are composite. And they will be just because of the form of this, all right? Now let's just change it one little bit. What if we chose n equals to 4? Okay, if we chose n equals to 4, we'd end up with 4. Add 12 to that, you get 16. See, and this would be an example where there would be no primes. And again, not rigorous by any stretch of the imagination, but hopefully convincing. 40, you can be very formal about this, but I'm just giving you a couple of examples here. So you see, this is going to be an infinite list of composite numbers. There won't be a prime in here, and you can tell by the form that that's true, right? Okay? So that sort of is an example. And I like this proof. It came from Charles Vanden Eynden's textbook. I'll put that in the description. It was problem 10 in the section on the infinitude of the primes, I think. But it's a nice way to get used to notation. It's not a hard problem. There's nothing deep about it. You know, you don't have to connect with any deep results. It just follows immediately from the definition of congruence and GCD, this proof. Okay? I think he concurs.